Alright, so we talked about parent functions already. A parent function is an original function with no changes to the graph. Okay, an original function with no changes to the graph is what we call a parent function. We have what we call family of functions, parent functions, and then we will transform those parent functions. Alright, a family of functions is a set of functions whose graphs have basic characteristics in common. Okay, so a set of functions whose graph have basic characteristics in common is our family of functions. So an example of a family of functions would be linear functions. Linear functions, okay, all have certain characteristics in common. They all make lines. They're all linear functions. They're all to the power of 1. A parent function is the most basic graph in that family, okay, or function in that family. So a parent function is the most basic function or graph in that family, meaning that it is in its original form. There is no changes to it. Now, to change it is what we call transform. Right? So you've all seen the movie Transformers. Okay, so it's a car, but then all of a sudden, now it's a robot. Right? It changed. Well, the car is the original function, and then it changed to a robot. Same thing here. So the transformation, okay, is going to evolve. It's going to change somehow my parent function. Alright, so a change, a transformation, is a change in either the size or the position of a figure. Okay, so a transformation is a change in either the size or the position of a figure. Alright, so again, we have our parent linear function, which is the function y equals x. That is our parent linear function. Okay, we could also write that as f of x equals x. These mean the exact same thing, guys. This f of x function notation is a fancy way of me writing y. So don't freak out. Okay, so this is a parent function for the linear function. So this is in slope-intercept form, which again is y equals mx plus b. How do I know? Because the y is by itself. It's isolated. So looking at the difference between this and this, I can pull my slope and I can pull my y-intercept. So for my parent linear function, Amira, can you tell me what is the slope? What is m in this equation right here? It's in this form, y equals mx plus b. So y equals x. So I'm looking at the number, m is the number in front of the x. So what's in front of that x? Yeah, a 1. Thank you, Amira. Okay, so it's a 1 in front of the x, right? So the slope is 1. Slope is 1. Okay, this is the parent function. This is the characteristics for a parent function. Okay, so now, Amira, what is the b? So y equals mx plus b. So what number is after the x, Amira? Plus 0. So the b is the y-intercept, right? Okay, so now help me out. What is the point? 0, 0. Okay, thank you, Amira. All right, so I know that it crosses the origin. The y-intercept's at the origin. So that's the first characteristic for the parent function for a linear function. I also know that it has a slope of 1. So it's going to rise 1, run 1. Rise 1, run 1. Rise 1, run 1. Rise 1, run 1, etc. Now, any graph that does not cross the origin, or any graph that does not have a slope of 1, is a change, a transformation to this function. Okay, so any graph that crosses at the y-intercept up here at positive 4, or down here at negative 2, is a change to to that function right there. Any graph that has a slope that's greater than 1 or less than 1 is a change to that function right there. So let's talk about our first transformation. Our first transformation is what we call translation. To translate means to move. Okay, so translation of linear function. We're going to move linear functions. Alright, so I've graphed 4 lines for you here. This line right here is the parent function. It crosses the origin, and again, it's got a slope of 1. So up 1, over 1, up 1, over 1, up 1, over 1. Okay, so now it says, refer to the 4 functions on the right. What similarities and differences do you see? What do you notice about all 4 of those functions, guys? They're all what? They're all parallel. Okay, so all the functions are parallel. Well, going back to yesterday, guys, what does that mean?
They all have the same slope.
So they have the same slope. So we know right now that we're not changing the slope because they all have the same slope. Otherwise, they're not going to be parallel. You getting this, Amir? So we know that they're all parallel, meaning they have the same slope. But what about their y-intercepts? Are they the same? Yes or no? They have different y-intercepts. So they're all parallel, they all have the same slope, but they all have different y-intercepts. So going back to slope-intercept form, what are we changing? What are we going to change? I told you they have the same slope, but they have a different y-intercept. So what variable are we changing? B, because B is the y-intercept. Again, this is y equals m. M is the slope. We're not changing that. They're parallel. They have to have the same m. They have to have the same slope. But they're going to have different y-intercepts. So they're going to have different numbers for B. Alright, so let's look at my examples here. I've got y equals x. Again, that's the linear parent function for a linear function. This is the function f of x plus 3. Well, what you notice that at the end, the b is now plus 3, whereas it was 0. This is plus 0. So what do we do? Well, the y-intercept moved up 3. So we translated it up 3 units. These say f of x, or I could say x, whatever you want to say, minus 2. Well, that went from a positive 0 or a plus 0 to a minus 2. So we went down 2. We shifted it down 2. We translated it down 2. Same thing here. We translated it down 4. So what am I changing when I'm translating? I'm changing the y-intercept. I'm changing the y-intercept when I translate. I don't touch the slope. The slope remains the same because they are parallel. But to translate it, I am changing the b. I'm changing the y-intercept. Okay, so let's look at an example. It says graph f of x and then graph g of x. F of x is my parent function, which again has a slope of 1, right? The number in front of the x. And it goes through the origin, 0, 0. So we graph that function. Looks like this. Okay, now I want to graph g of x equals x minus 3. Okay, so Aiden, what is the slope for g of x? 1. Okay, so my slope is still 1, but what is my b? What is my y-intercept? Okay, so it's at 0, negative 3. Fantastic. So the first thing I'm going to do is I'm going to plot my y-intercept, which is at 0, negative 3. And now I'm going to go with my slope. My slope is rise over run. So I'm going to rise 1, run 1, etc., etc., etc. So this is f of x equals x this is g of x equals x minus 3. Alright, so I've plotted my two graphs, right? I've plotted my two functions. Okay, so Zuyer, help me out. What did I change? I changed the y-intercept. Okay, it went from what? 0 to -3. So what did I do? I moved it down 3 units. Okay, so we say we translated it down 3 units. Again, the slope didn't change. Those two lines are parallel. Those two lines are parallel. The slope didn't change. They have the same slope. But I moved it down 3 units. I translated it down 3 units. So the y-intercept went from 0, 0 to 0, -3. Okay, the way to note it is g of x equals x minus 3. It could be written as g of x equals f of x minus 3. So translations are a change in the y-intercept, a change in b, a change in the y-intercept. Transformation. Okay, I'm translating it. The second transformation that we're going to talk about is a dilation. A dilation. Okay, so once again, I've graphed 4 functions for you. What do we notice about all 4 of those functions? They're not all intersect at a 90-degree angle. So they're not perpendicular. They all intersect, yes. They all have the same what? Y-intercept. They all have the same y-intercept, meaning they have the same what variable? B. They all have the same B. They all have the same y-intercept. But they have different what? Absolutely. So what variable is going to change for a dilation? What? Not x. M. M is the slope, which again is the number in front of the x. Right? So they all have the same y-intercept. They all have the y-intercept at 0, 0. B is 0, 0. But they have different slopes, different m's. So let's look at my parent function, which is y equals x. We have 2 dilations. We either have a vertical stretch or a vertical compression. And what you're going to look at is you're going to look at the number for the slope. The number for the slope. Again, my parent function has a slope of 1. So we're going off of 1. If the number is greater than 1, then it is a vertical stretch. Okay, let me say that again. If the number is greater than 1, it's a vertical stretch. So I'm reading right here. If f of x is greater than 1, we call this a vertical stretch. So imagine with me that I'm going to pull this vertically. Right? I'm going to grab this line, I'm going to pull it vertically. The bigger the number, the graph is going to go higher, right? Because this is 2, this is 4. So I'm pulling it vertically, I'm stretching it vertically. So the bigger the m, the bigger the slope, greater than 1, it's a vertical stretch by a factor of whatever that number is. So this is by a factor of 2, this is by a factor of 4. So to stretch it means that the number is greater than 1. To compress it means that the number is less than 1. So if I have a fraction for my slope, that will be a vertical compression. It will be a vertical compression. Right? So 1/4 is less than 1. 1/4 is 0.25. That's less than 1. So if the number is less than 1, it's a vertical compression. It's going down. It's not as steep. The bigger the slope, the steeper the graph. Again, vertical stretch. We're stretching it vertically. The smaller the slope, fraction, less than 1, the flatter the graph. We call that a vertical compression by whatever the factor is, by whatever that slope is, which in this case is a 1/4. Okay, so let's look at some examples. It says graph f of x again, so my parent function, and then graph 2x minus 3. So here's my f of x function. And then now we're going to graph the function 2x minus 3. 2x minus 3. Okay, so again, what I want to pull from here is I want to pull the slope and I want to pull the y-intercept. I want to pull my starting point. So Taylor, help me out. What's the y-intercept for 2x minus 3? Again, this is y equals mx plus b. M is your slope. B is your y-intercept. So for this function, g of x equals 2x minus 3, what is the y-intercept? Y equals mx plus b. B is the y-intercept.
Oh, okay, so I thought you asked me for 3.
Okay, so it's at 0, negative 3. So I'm going to start there. I'm going to plot that point. So I'm going to go over 0. I'm going to go down 3. 1, 2, 3. There's my y-intercept. So right now, I know a transformation. What happened? Can you tell me what happened, Isabel?
It went down 3.
It went down 3. So we translated it down 3 units. Well, how do I know that? Well, the y-intercept went from 0 to negative 3. So I translated it down 3 units. So there's a first transformation. Okay, now we also know that the slope changed. The slope was right here at positive 1, and now the slope's at 2. So my slope is 2. So Callie, slope is rise over run, right? So we're going to go up 2 over 1. Up 2 over 1, up 2 over 1, up 2 over 1. So my graph looks like this for g of x. So Callie, talk to me. What is the second transformation? We know that we changed the y-intercept when we went down 3 units. We also know that the slope changed. The slope went from a 1 to a 2. So you've got 2 choices, Callie. It's either a vertical stretch or a vertical compression. Because again, the greater the number, if it's bigger than 1, it's a vertical stretch. And 2 is bigger than 1. Last I checked. Always. So the second transformation is it's a vertical stretch. By a factor of what, Callie?
2.
Yeah. Fantastic. So again, we could say that g of x equals 2x minus 3, or it could be 2f of x minus 3. So looking at my 2 functions, guys, we had y equals x, and we had y equals, because again, g of x is just a fancy way of me saying y, so don't freak out, y equals 2x minus 3. Well, I can look at my 2 functions and see there's 2 changes. The first change is right here. That changed. There's nothing after this x. Now there's a negative 3. Well, guess what? That changes the y-intercept. We translated it down 3 units. We can look at the second change. That's right here. There's a 1 in front of that x, but now it changed to a 2. So my slope got bigger. My slope gets bigger. It's a vertical stretch by a factor of 2. So in that problem, there were 2 separate transformations. Last transformation we're going to talk about is a reflection. Okay, a reflection. So what comes to mind when you hear the word reflection? Looking in the what? Mirror, right? Because if you look in the mirror, you see a reflection of yourself. It's the exact same thing, except it's backwards. Okay, so it's a reflection. It's the exact same thing, but it's backwards. What we call a reflection. So looking at my graph here, guys, this is f of x equals x. This is my parent function. This is f of x, or g of x, excuse me, is negative x, or negative f of x. So all I did was make my function negative. All I did was make my function negative. Okay? So now, what do I notice about the slope of this line right here? Nora, what do you notice about the slope of that line right there? It's a positive slope. But what about this one? Yeah, so one has a positive slope. The other is negative. So one is increasing, one has a positive slope, the other has a negative slope. It's going down, it's decreasing. But are they the same number? Yeah, they're both 1. One of them's a negative 1, but they're the same number. This is a rise 1, run 1, rise 1, run 1. Guess what? This is a rise, or down 1, run 1, down 1, run 1. So they both have a slope of 1. It's just one of them has a slope of negative 1. One of them's negative. Alright, so when I take the negative of the function, it's a reflection across the x-axis. Across the x-axis. Okay, so across this line right here, I'm going to reflect that. So what does that mean? I'm taking this line, okay, and I'm reflecting it. I'm flipping it over across that line right there. Okay, so this point, when I flip it over, is going to map to this point. This point up here, when I take it and I reflect it, I flip it over, is going to map to this point. Do y'all agree? Yes, no, maybe. Okay, and I can keep going. This point would map to this point. Well, let's look at it. Let's look at it mathematically. Okay, so this is the function y equals x. This is the function y equals negative x. So we're going to plug in a point, right? So if I plug in 1, my x value, into this function, what do I get for the y value? If I plug in 1 right here, what do I get for y? No, right here. If I plug in 1, y equals 1. So you got to point at 1, 1. What about if I plug in 2? Plug in 2 for x. Y equals, so I got to point at 2, 2, which is where I'm getting those points from. Okay, but now let's look at this function. I'm going to plug in the exact same numbers. Okay, so I've got an x value of 1. So when I plug in 1 right here, y equals what? Negative 1. So my point is at 1, negative 1. Look at that. What about when I plug in a positive 2 for x? Y equals negative 2. So you got to point at 2, negative 2. Okay, so it's reflecting across the x-axis. So all you got to do, guys, is figure out how far away from the x-axis it is. Go to your x-axis and go down that much. This one is 2 units away from the x-axis. Okay, it's up 2. So guess what? Go to the x-axis, go down 2 units. That's the point that corresponds to it. Same thing, this one's 3 units above. Guess what? Go down 3 units from the x-axis. That corresponds to it. Reflection across the x-axis. When I put a negative in front of my function, it reflects across the x-axis. When I put a negative in front of my x, in front of my function, it reflects across the x-axis. Okay, so last page. Here we go. Multiple transformations. I'm going to graph my parent function, which again is f of x or y equals x. We know that it's got a slope of 1. We know that it has a y-intercept at 0, 0. So there's my parent function. Okay, now we want to graph the function g of x equals negative 4x minus 1. Negative 4x minus 1. Okay, so Michael, help me out. This is in y equals mx plus b form. It's in my slope-intercept form. So I want to know, what is the y-intercept? What is b? Negative 1. Okay, so now what is the point? What point am I plotting? Because the first thing I need to do to graph something is to plot my y-intercept. So I know that my y-intercept is negative 1, but that's not a point. What's the point that's associated with that? No, babe. Negative 1. Can somebody let him in? Zero. Yeah. No. 0, negative 1. You don't want to go over any. Okay, we're on the y-axis, right? So y-intercept. So it's 0, negative 1. So your y-intercept is 0, negative 1. All right, so that's the first thing. Plot your y-intercept. So we know right now, Michael, what changed? We already know one of the transformations. What is it? Yeah, what happened? Down how many? Down 1. So we translated, because again, translate means to move. We know what we translated, down 1 unit. Fantastic. Okay, so that's the first transformation. Because again, we changed the y-intercept. Anytime you change the y-intercept, you're either going up or down. Okay, and we went negative 1, so we went down 1 from 0, right? It went from 0 to minus 1. So obviously we went down 1. So first transformation, it translated down 1 unit. Let's look at our second transformation. Okay, our second transformation. My slope, okay, I'm looking at my slope, went from a 1 to a 4. Okay, it went from a 1 to a 4. So Ryan, is that 4, is it bigger than 1 or less than 1? Okay, so if it's bigger than 1, we call that a vertical stretch or a vertical compression. So I know that my second transformation is a vertical stretch by a factor of what? Fantastic. Yep, what's up, Dave?
Why would you say 1 instead of negative 4?
Because the negative does something else. That's the third transformation. That's what I just talked about for the last 10 minutes. So it's a vertical stretch by a factor of 4. Okay, now, if I want to plot my line, then yes, David, I need to go my slope, which is a negative 4. So I'm going to go down 4. 1, 2, 3, 4 over 1. Okay, I can go backwards. I can go up 4 to the left 1. So there's the line for g of x. So I have 2 transformations thus far. Okay, we know that my y-intercept went from 0 to negative 1. So we translated it down 1 unit. We know that the slope went from a 1 to a 4. 4 is bigger than 1. Anytime the number is bigger than 1, it's a vertical stretch. Anytime the number is less than 1, it's a vertical compression. So a vertical stretch by a factor of 4. Okay, so David, can you tell me what that negative does in front of that 4? Can you tell me what that negative does in front of that 4? Yeah, because right here, my example was f of x equals x. That's positive, right, David? Okay, and then I changed to g of x equals negative x. Right, so I made it a negative. And what did it do? It reflected across the x-axis. Same thing here. My graph went from a y equals x to y equals negative 4x minus 1. So we reflected across what, David? Across the x-axis. So there were 3 different transformations on that graph. I translated it down 1 unit, I changed the b. I changed the slope, it went from 1 to a 4, and I made it negative. Vertical stretch by a factor of 4, and I reflected across the x-axis. So we've got 2 more examples to work, guys. I'm going to graph my parent function. There it is right there. And then now I'm going to graph g of x. So g of x equals 1/2 x minus 3. 1/2 x minus 3. Again, we're looking to graph functions. The first thing I need to do to graph a function is to plot my y-intercept. So Lucas, help me out. What's the y-intercept?
1/2.
Guys,
Oh, y-intercept, sorry, 3.
I don't know, but you're not the only one that's done that. And everybody was doing that in my first period. I don't understand why y'all are getting this screwed up. Y equals mx plus b. Right? So anytime I ask for the y-intercept, I look for the number at the end. Anytime I look for the slope, I ask for the number at the beginning. Okay, maybe I didn't do a good job explaining myself. The y-intercept is the number after the x. After the x. The slope is the number before the x. Alright, so 0, -3. Fantastic. So let's plot that point. Okay, and then from there I'm looking at my slope. My slope is up 1 over 2. Rise over run. So I'm going to rise 1, run 2. Rise 1, run 2. I can go backwards, go down 1 over 2. So there's the function g of x. F of x. Alright, so again, this is f of x, or I could say y equals x. And then g of x, which again I could say y, equals 1/2 x minus 3. So looking at those 2 functions, Aura, how many transformations do you see?
Let me see.
2. Okay, tell me, what were those 2 transformations?
We had a change in the y-intercept and
Fantastic. So we had a change in this number right here because it was 0 and now it's a -3. And we had a change in the slope. Right now it was a 1 and then it changed to a 1/2. Okay, so let's look at the y-intercept first, Aura. That is what we call a translation. So it translated what? Down 3 units. Fantastic. Translated down 3 units. Okay, Aiden. Now we're looking at the slope. The slope went from a 1 to a 1/2. What was the second transformation, Aiden?
It was vertically compressed.
Fantastic. By a factor of what?
1/2.
Great job. So again, if the number is less than 1, guys, it is a compression. So 1/2 is 0.5, which is less than 1. So it's a vertical compression by a factor of 1/2. If I wanted to write this in function notation, it'd be g of x. Okay, g of x equals 1/2 f of x. All I'm doing is plugging in my function, minus 3. Okay, this is what I'm worried about, guys. Understanding that there are 2 transformations to that graph. So I'm going to give you about a minute. Okay, I want you to work on number 5 by yourself. So we're graphing the parent function. And I'm going to give you a hint. There are 3 transformations to that parent function. There are 3 separate transformations to that parent function. I need you to tell me what those 3 transformations are. So it's f of x equals x. And it's h of x equals -3x plus 1. So you're going to tell me what those 3 transformations are. Okay, so again, it's a vertical stretch because the number went from a 1 to a 3. So it's a vertical stretch by a factor of, what's that number? 3. So anytime your slope changes, it's a vertical stretch or a compression. Anytime your slope changes, vertical stretch or a compression. In this case, it's a stretch because the number is greater than 1. 3 is greater than 1. Vertical stretch by a factor of 3. Great job. Michael, can you tell me another transformation? So the y-intercept changed, and it went from plus 0 right here to plus 1. So we went up 1, right? So we call that a, well, yes, but it's translated, okay, translated up 1 unit. So the y-intercept went from 0 to 1, all right? So let's plot that point, because again, the b is at 0, positive 1. There it is right there. And Noor told me it has a slope of negative 3, so we'll go down 3 over 1, down 3 over 1. So there's the graph g of x, or h of x, sorry. So there's one more transformation. One more transformation. Or can you tell me what that third transformation is? Fantastic. Because again, that is negative. Right? It's negative. So it's reflected across the x-axis. And to write that in function notation, guys, I'd be writing h of x equals negative 3 f of x plus 1. So again, you're going to compare these two functions, right? So tell me what changed in those two functions. Well, the b changed. It was at 0. Now it's at a plus 1. What does that mean? It means I translated it up 1 unit. The slope changed. It was at 1. Now it's at 3. Bigger the number, it's a vertical stretch by a factor of 3. And then last but not least, it was a positive slope. It changed to a negative slope. Therefore, it's reflected across the x-axis. Okay, so we have 3 different transformations that we learned. A translation, a dilation, and a reflection.